So we were talking about testing and debugging, and in this we were discussing this boundary value analysis. And what happens in boundary value analysis? We have already seen the first approach in black box testing, and that was our equivalence partitioning. In this boundary value analysis, some typical programming errors may occur, in our software product. So at boundaries of equivalence classes, this might be purely due to psychological factor, physiological factors, but programmers may oversight it, or they may often fail to see it. That special processing are required of equivalence classes. So special processing at the boundaries of equivalence classes. We have made equivalence classes. We have seen examples of equivalence classes also. For example, programmers may improperly use say greater than instead of greater than equal to, or less than instead of less than equal to. So boundary value analysis, as the name is itself suggesting, that the values at the boundary of the input stream, the analysis of this. So we select test cases at the boundaries. We take equivalence classes and then we select the boundary values. For instance, for a function that computes the square root of a integer in the range 1 to 5000, the test cases must include the value. What values? 1 and 5000. These are the boundary values. A value which is below 1, a value which is above 5000. So these are the boundary values, and values which are above and below these values must be included. Once the errors are being identified, what is the next task? We have to remove this. So it is necessary to identify the precise location of the errors also, and then to debug or fix them. Each debugging approach, there are several debugging approaches. They have their own advantages and disadvantages. And for appropriate circumstances, one may be useful, one may be not. Let us take a brute force method. This is the most common method of debugging. Quite least efficient, and program is loaded with print statement, message boxes, or traces, or various others, couts. So it print the intermediate values and hope that some of the printed values will help identify the error. So we flush or we feed the print statements inside. This is brute forced. In symbolic debugger, this brute force approach, it becomes more systematic. We use symbolic debugger, and why this name is, it has received its name for some historical reason. Early debuggers let you only see values from program dump or some log. So there will be a dump that will be created that determines the variable it corresponds to. Now we have various debuggers inbuilt in our IDE where we can find out the actual problems or the values. So if we use a symbolic debugger, the values of different variable can be easily checked and modified. And also single stepping to execute one instruction at a time. This can also be done how? We can enforce or we can introduce breakpoints or watch points, and this can be set to test the values of variables, breakpoints and watch points. Then we talk about the debugging approach, that is backtracking. This is fairly most common approach that is being employed. So we start or beginning at the statement where an error symptom has been observed. We start from there, and the source code is then traced backward until the error is discovered. So we begin at the statement where this error symptom have been observed, because the error may be somewhere else, or the error may be propagated to this statement. So we start with this statement, we go backward until we point out where the actual error is observed. In C program, if you just miss a semicolon, there will be hundreds of errors. Okay, so that 100 of error, that doesn't mean you have 100 errors. That only means that there is some error which is propagated, and that is why you are seeing these 100 errors. Just for example, we can take that this is main ijs I equal to 1, I less than equal to 10, s is equal to s plus I plus plus, j plus plus, printf percent d in s. So you are trying to print in the value of s. So can you point out the error if at all? See, I is initialized to 1, but s has no value here. So what will s be printing? So that will be printing some garbage value. And also you are assigning j to j plus plus. J is also not initialized. So when some error would occur, you backtrack and you go back and you see, okay, what was the error? This is the way we backtrack. But unfortunately, as the number of lines or source lines they increase, you know, as the number of source lines to be traced back, it increased to a level where it becomes unmanageable. The number of potential backward path they increase tremendously, and it becomes unmanageably large for complex programs. Then we come to cause elimination method. We determine or list some causes which can possibly be the culprits. They have contributed to the error system. So tests are conducted to eliminate each. This listing, which what we have done. So we list them and then we try to test to eliminate each of them. A related technique of identifying error just by examining error system. This is software fault tree analysis. This software fault tree analysis is also doing the same stuff. Then we come to program slicing. This is again similar to backtracking we have discussed, but the search space is reduced. The problem with backtracking was if the number of source line will increase, then the problem of managing it will be there. So search space is reduced by defining slices. What are these slices? The slice is defined for a particular variable at a particular statement. So the set of source line preceding this statement which can influence the value of the variable. This is how it has been sliced. And now we see that what could be the potential way of addressing it. You know that I is okay, but S you need to really see. So debugging guidelines, because we have to debug and we have to have some guidelines. It requires that you should have a thorough and clean understanding of the program design. You are required sometime to fully redesign the system. You may be doing that because if you don't redesign it, then bug will remain. The common mistake new programmers they make, that they fix the error, not fixing the error, but the error symptoms. This is like going to a doctor and saying that I have this problem, I am having fever. So he just give you a crocin or a paracetamol for your fever, but not going to the detail what has happened, what was the history. So knowing all these is important. Just be aware of the possibility, and error correction may introduce new errors. That is why we know a term called regression testing for it. And after every round of error fixing, we regress. That means we perform regression testing that this error fixing has not created any more errors. Then we have various program analysis tools, automated tools also, that just takes program source code as input and it produces reports regarding several important characteristics of the program, like your rational products of IBM, and then you have LDRA. All these are doing this only, and they also produce this size, complexity, adequacy of commenting, adherence to various programming standards like MISRA, JSFs, etc. These are programming tools. They produce reports regarding to the adequacy of the test case. They also test whether test cases are adequate or not. So there are essentially two categories of program analysis tools. First is your static analysis tools. The second is dynamic analysis tools. For static analysis tools, you don't need to run the program. And for dynamic analysis tools, you need to actually execute the program. So static analysis tools, it assesses the properties of the program with respect to the standard or with respect to the programming language itself without executing it. You don't need to run the program. And it just analyzes the source code and it provides you analytical conclusions. And if you are saying that I'm conforming to certain coding standards, then they will check it. Just for example, say commenting is adequate or not. So programming errors such as uninitialized variables, mismatch between your actual and formal parameters, variables are declared but they have never found their way to be used or employed. These are the static analysis results. See, so code walkthrough inspection can also be considered as static analysis tools. But the term static analysis or static program analysis is generally related to or in context to automated analysis tools. Also we talk about it. What about dynamic analysis tools? These dynamic program analysis tools, they require the program to be executed, actually run. So its behavior is recorded and then the reports are produced such as adequacy of your test cases. Then we come to actual testing. The aim of testing is to identify all the defects in a software product. The testing is done with an aim to find an error or a bug. In practice, even through thorough testing, you cannot guarantee that the software is error free. The input data domain of most software project is quite large, and it may be impractical to test the software exhaustively with each input data value. This is impossible. So testing does, however, exposes various errors. I should say, I cannot give you a number, say 99%, but many errors. So testing provides a practical way of dealing, identifying, removing the defects, and it increases the user confidence. It increases the user confidence in a developed system that certain programming standard was followed and it was adhered to, and these testing were performed, and these are the results. So testing in a development phase is an important part. It requires the maximum effort among all the development phases. In a typical development organization, most of the software engineers you will see will be engaged in testing activities only. And various software people, they have a wrong impression that testing is a secondary activity. It is not. It is actually a primary activity. It is intellectually not as stimulating as other development activities. It is not, because if you are making a software and it has some bug, the business and everything is going to be spoiled. Testing of a product is more challenging as the development activities such as specification, design, and coding. So testing involves a lot of creative thinking. If you are not creative, if you are not thoughtful, if you are not intellectual, you cannot perform this testing. So software testing, they are tested at 3 levels. We are going to talk about these each in the later section. But unit testing, integration testing, and system testing, these are the main 3 categories or types of testing. So I hope we have introduced this testing and seen how debugging options can be there. And we'll be talking about this in the other section. Thank you so much. Take care.